Logistic regression is different from linear regression in the sense that dependent variable in the logistic regression is binary. That is, it will take one of the two values, event happening or not happening. While in the linear regression, the dependent variable is continuous. In this video, I'll talk about how to perform a logistic regression in R. So let's take a look at very simple example. Let's say we have a credit card data which looks like this. So you see here we have four variables: credit history, employee tenure, income, and good and bad. Good and bad is the dependent variable. It takes two values, 1 and 0. 1 stands for the good customer, that is a non-defaulting customer, and 0 is for the bad customer. Credit history, employee tenure, and income are the independent variables. So first of all, let's read this file into R. It's a CSV file, so we'll be using read.csv command to read this file into R. So let's read it. So I'm using the read.csv and I'm storing this in a data frame called credit. Now let's take a look at the structure of this credit data frame. As you can see, it has 1000 observations and 4 variables, and all the 4 variables have been read into R as an integer. So that is how my data looks like. Now to fit the logistic regression in R, we use the GLM command. GLM stands for generalized linear models. So let's run this command and store the output from the GLM command into an R object called myResult. So if we'll print the myResult, that is how the output looks like. If you look at here, it basically, first of all, R gives us the basic formula which we have given in the GLM command. If you notice, in the GLM command I've given 3 options, 3 arguments. First argument is the formula for building the logistic regression, in which good bad is the dependent variable, and in credit history, income, and employee tenure, they are the independent variable. Second argument, I'm mentioning the data frame from where the R will search for those variables. And third option, as family, I'm writing binomial for this option. Binomial because we are running the simple logistic regression which has only 2 outcomes. It's a binary outcome, so that is why we are mentioning here family as binomial. So this is the first part which myResult has it, or R prints out. Then the second part which is printed here is the coefficient values, and in the third part R gives us null deviance and residual deviance together with the AIC value. This is the basic summary which R is giving us, but if we want to know more about the summary, then we can print the summary command, or we can just type the summary of myResult. So if we'll type down the summary of myResult, it will give us summary for all the whatever is in there in the myResult R object. So what it gives is, it first of all it tells you about the model we have run. That means it gives you the formula, and then the data frame, everything it prints out. Then it tells you about the deviance residuals. If you look at the second option, second output here, second thing which it prints out is the deviance residuals. They are actually the residuals from logistic regression, but they are not very useful as we fit the logistic model with the maximum likelihood function. So these residuals are calculated using the likelihood functions. The formula to calculate the deviance residuals is different from the regular residuals, but they can have properties similar to regular residuals. For example, they can be symmetric. So for example, if we look at this one which is printed here, then our residuals or deviance residuals looks like roughly they are symmetric. So this is what it prints out. After that, R gives us the coefficient estimates. These coefficients are again estimated through the maximum likelihood estimates. Then it also gives us the standard errors related to these coefficients. Then it gives the z-value. Z-value is nothing but it is obtained by dividing the value of the coefficients with the standard error. Then it also prints the p-value or the probability for these coefficients. The output of the logistic regression is same as the linear regression. The difference is we predict logit scores and not the outcome measures directly. That is what the difference lies. So for example, let's take a look at the first coefficient or the intercept, if you look at it, the coefficient value is, or the intercept is, negative 0.487. It's actually the logit score of non-defaulting when the employee tenure, credit history and income is 0. If next look at it, the coefficient of credit history, the value for the coefficient of negative credit history is 0.49. Now this simply tells us that what is the increase in the logit score of non-defaulting when there is a unit change in the credit history. The z-test for the coefficient of credit history gives us a very small p-value, indicating that the data is not come from a population where the null hypothesis is true. That is, where there is no relationship between non-defaulting and credit history. In other words, we can say that there is a relationship between credit history and non-defaulting behavior of a customer. Now if we look at the p-value for the coefficient of income, then the p-value is 0.28. So this is basically telling us that this p-value is not significant and the data is come from a population where the null is true. That means we can say that there is no relationship between income and the non-defaulting behavior of the customer. Similarly, if we look at the p-value for the coefficient of employee tenure, it is also 0.19, which is not significant. So we can say that employee tenure is not important in predicting the non-defaulting behavior of the customer. So in this model, the only significant coefficient for the prediction of a non-defaulting behavior is credit history. So this is what the output for the coefficient is given to us. Now logit score is something which doesn't have an easy interpretation. So to interpret these results, what we can do is we can convert these logit scores into odds. First of all, we'll convert them into odds and then we'll look at the probability values as well. Now in this particular example, which I've taken it here, the only significant coefficient we have is the credit history. And the coefficient or the logit score is 0.49. So that means we have a logit score for the non-defaulting is basically 0.49 times credit history. Or let's say if a person has a credit score 5, then for that particular person the logit score for non-defaulting will become 0.49 times 5. So if you multiply, that gives us 2.45. So this is the logit scores. Now to obtain odds from the logit scores, what we can do is we can exponentiate these logit scores. So if we exponentiate 2.45, the value we get is actually 11.58. So you can see here the value we are getting. So this is the value of the odds. So this is what we are getting. Now odds, just to remind you that odds is what? For an event, odds is probability of an event happening divided by probability that the event will not happen. So let's say if odds are 1, then there are 50% chances that event is going to happen and 50% chances that event is not going to happen. So if odds are more than 1, then it is more likely that the event is going to happen. So in this particular case, if we look at the odds value, it is 11.5, which is much greater than 1. So we can say it is more likely that the person is not going to default when his credit score is 5. So that is how we interpret odds, or that is how we look at the odds value. In this, from odds value, we can actually calculate the probabilities also, but to calculate the probability, we still have to do little bit more calculation. So recall that probability, how we calculate probability from odds is by, we divide odds by odds plus 1. So this gives us the probability value. And if we do so, so that means in this particular case, when the odds come out to be 11.58, I just have to divide 11.58 from 12.58 and this will give me the p-value. So if we calculate this p-value, the p-value comes out to be 0.92. So this means that there are more than 90% chances that a person with credit history 5 is not going to default. So that is how from credit score we look at the odds and we also look at the probability value, which are easier to interpret. Now if we look at the summary one more time, then after the coefficients, R prints us, R gives this null deviance and residual deviance. Now deviance represent the error after the prediction have been, or the predictor have been accounted for. Now it is analogous to the sum of square error in linear regression. So null deviance shows the deviance of the model without any predictor, and residual deviance shows the deviance of the model with predictor. Actually, these are the chi-square values with the given degrees of freedom. So to know whether the model with predictor is useful or not, what we usually have to do is simply calculate the chi-square probability. Given these chi-square values, for null deviance it is 1,222.7 and for residual deviance it is 1166. So from these chi-square values, I can just calculate the chi-square probability by using a p-chi-square, p-chi-sq function. And what I'm doing here is just taking the difference between these two chi-square values and taking the difference of the degrees of freedom. And since I'm interested in right tail probability, so I'm setting up as lower tail as false. This gives us the probability value of 2.9 times 10 to the negative 12. This is exceedingly small. So this p-value indicates that there is a statistically significant difference between the model without predictor and the model with predictor. Or in other words, we can say that predictors are useful in predicting the non-defaulting behavior of a customer. So that is how we can look at our model, that how it is performing, by looking at the null deviance and the residual deviance. The last value which the summary gives us is the AIC value, or the Akaike information criterion. The basic idea is it tells us by adding more variable to the model, what we are doing is we are adding little information to the model. But at the same time, we might be overfitting it. So the model might not perform well for the new data. So this simply means that the lesser the value of AIC means the better the model is. So that is how we interpret this AIC value. The value should be less. Now these are the output generated by the summary command when we look at the output of the GLM command. Now so far we have seen, by looking at the p-value or the probability value from those null deviance and residual deviance, that how or whether my predictors are useful in prediction of the dependent variable or predicting the values of the dependent variable. Now to know how my model is fitting the data, one way to know this is by plotting the values of these variables. So what do I mean by that is, well, let's plot, first of all let's plot the independent variable and the dependent variable. That means independent variable in this case is the credit history, and the dependent variable was the good bad variable. So let's plot this one first and see how actually these two are looking like. So if you plot this, that is how the graph looks like. So as you can see that given a credit history, good bad score can be either 0 or it can be 1. So that is how my actual data looks like. Let's see how the predicted values are going to look like. So if I am again plotting a credit history with the predicted values given by my result, then let's try to plot this one. Now if I'm trying to plot this one, I see an error is appearing, and the error is basically saying that X and Y lengths differ. This simply means that the variable credit history and the fitted values or the probability values from my result, they are different in length. So to solve this one or to look more into it, what we'll do, we'll look at the length. So let's take a look at the length of credit history. It is 1000. Now let's take a look at the length of predicted values from my result. So if you look at this vector has a length of 999. So as you can see that there is a difference in length, and this is the reason the command was giving us an error that the lengths are different. Now why this difference is appearing? Because there is a missing value in my data. So while modeling, GLM command is omitting that observation while fitting the model. An observation where a missing value is appearing, GLM is not taking into account that particular row. So let's take a look at which row has the missing value. To know that which row has a missing value, I'm using a complete.case command. Actually, what does a complete.case does? Complete.case gives you all those rows or all those observations where there is no missing value. So when I'm negating it, I'm going to get all those rows where we are having the missing values. So in this particular case, when we are using this command for this particular data frame credit, I can see that row number 517 has a missing value. and this is the reason this particular row was not taking into account when the model was formed, and we are getting a different length. So what we can do now is we can create a new variable. We can remove this row from our credit history variable, and let's remove it. So after removing it, I'm calling the new variable as credit history.noNA. So I'm storing result in there. So let's look at the length of credit history.noNA. As you can see now that it has a length of 999. So both the variables now they have equal length. So we can plot. So now let's try plotting it. So we are plotting it. Yeah, there we go. So you can see that is how my fitted values looks like. So blue dots are the actual values for good bad, and these red circles are the predicted values. And you can, from there you can judge that how your model is performing in this particular case. This is one of the way of judging how your model is performing.